Hello. Today we will see quantum gates. So for this, we can define each quantum gate manipulates output or a qubit states, providing a comprehensive understanding of their functionalities and outputs based on their different inputs. So each gate serves a specific purpose in quantum circuits, leading operations like superposition, entanglement, and phase manipulation. So let's see. When we see is like logic gate, we can classify types of logic gates like classical computing before say that, and next quantum logic gates. What are traditional logic gates? And logic gates like fundamental components in digital circuit as we know that perform like zero and ones. When we come to modern definition like logic gates, with this based on like quantum logic gates. This quantum logic gate we can define like a modern definition. Logic gates an operation transforms input data that to output data, which is classical binary as you know, zero and ones, or quantum, which is a quantum like superposition of states, and many may involve reversible competition. Next, we can see like a classification one a feature there types and competition and reversibility and implementation energy efficiency and key examples. This as a comparison between traditional or classical logic gates into modern quantum reversible logic gates. So when we see as traditional types like 0 1, and when modern we come to superposition or cubes, and when see competition features like deterministic and probabilistic on quantum. Reversibility, mostly irreversible. Mostly when we see modern, it's reversible. Implementation, transistors and IC for traditional. When we see modern, quantum circuits there, photonics and DNA computing. Energy level or energy efficiency consumes energy its dispersion. In modern level, reversible gates reduce energy loss. So what are the key example as is there for use we will see for the next slice, and or not XOR truth table or logic gate. When we see in modern or quantum, Admart, CNOT, TOEFL, quantum Fourier transform. Okay, so let's see the truth tables of classical logic gate. For this, as we see that the first one AND gate, only A value, B value, or the inputs are 1, it will get the output will be 1. For this is called AND gate. For OR gate, at least one, if it is true or 1, we will get 1. 0 0 0, this which means two promises are false, we will get false or 0. If it is 0 1 promise is false, the other one is true, the output will be true, which is 1. So at least one premise is true, the output will be true. Not gates, which is invert gate. If it is the input is 0, the output will be 1. If it is 1, the output will be 0 or false. And NAND is negation of AND, is when we 0 0, which is 1 0 1 1 1 is 0 is 1 1 1 0. NOR, negation of OR, is also the invert of OR. So 0 0 1 0 1 0 1 0 0 1 1 is 0. ZOR, which is 0 0 in this gate, exclusive gates, if it is the inputs are different, the output will be 1, otherwise false. As we see, is the input is different, the output will be 1, otherwise 0. How about quantum logic gates? For this, a single qubit like poly X, poly Y, poly Z, and unmarked. To determine the matrix in this like matrix representation, you will do that identifying the number of qubits. This is the base case. Determine how the case transform each base, filling the matrix based on the transformation. And finally, each entry corresponds to the output state when the gate is applied to specific input state. Hence, when we see the poly XX matrix like identity matrix, so let's see one by one. When we see here poly X gate, identify number of the output if the number of qubits is 1, right? So when with the base state like 0 qubit and 1 qubit, determine the action of the gates like X gate is equal to 0 1, the output is 1. X equals 1, the output will be 0. So when we represent this in matrix, like 0 here, we can put like this, and 0 in here. This is automatically X value and Y value, input value and output value. 0 and 1, 0 and 1. The output 1 0 1 0. That's it. Means input state is 0, we can flip the state of the qubit. Let's see. The initial state or the input state is 0. We can calculate and flip the inputs 0 to 1. So the output of this state is 1. Input state is 1. The calculation or the output of the X gate poly X will be 0. Flip the state of the input state. How about poly Y? Poly Y flips the state of the qubit and introduce phase shift. Let's see. If it is the input is 0, the Y is 0, remain unchanged. If the input is 1, the output is 1. Phase shifted, as we see. As we see, gate does not change the state if it is the state of 0 resulting 0. The gate introduces shifted. The result in the output is 1 associated with the vector that is represented imaginary y0, y1, y output is 0, which is imaginary units. So poly Z applies phase flip the output. When is the input state is 0, the Z value or the imaginary number is unstated, unchanged, so the output will be like that. We can use applies pi to 1. In Z1 it's -1. So the polygate does not change the state of 0. 0 is 0. When the output is, the input state is 1, the output is -1, which is added a phase of pi. Armored gate creates the operation state like the input is 0, the output will be this. One over root of 2, 0 key plus, which is the main difference between the 1 input and the 0 input. So when is 0 the input, which is plus, when we see here the 1 it is minus. So for input 1, which is 1 over root of 2, 0 minus 1. So the solution will be for 0, which is this, for 1, which is here. Phase gates S, which is shifted to pi to 2, 1. So the initial is 0, the output is 0, remains unchanged. For 1, which is imaginary y, added the phase of pi over pi, which is 1. C naught is the main controlled node, which is, so it has 2 initial states, which is 0, 0. The possibilities as we defined in classical logic gate truth table. In here we can apply here. So the target is only flip when it's the input is at least 1 at the last bottom. So flip the target if the control quibt is 1. Quibt is when we see this is the control state and the target state. 0 is control, 0 is the target, and if 0 is the control, 1 is target, 1 is control state, this is target state in quantum logic gate C notes. So we will at least when is flip the target, which means have you seen here 0 is target, 1 is target. So control state is 1, control state is 1. Immediately flip when the control state is 1. This is the C naught gate. So to here the number of qubits is 2. You can see here 2, 2, 2 number of qubits. Hence how to determine 0, 0 is 0 unchanged, 0, 1 is 0, 1 unchanged, as mentioned before. 1, 0 is changed, 1, 1 the target is changed, flips the output. Why? 1 is the control state. Here also again 1, 1 the control state is 1, immediately we will change the target state 1, change it to 0. So we can represent like this the C node in matrix state. And here's the last TOEFL gate or sys node. In here, only for both control keys are 1, immediately flips the target. How many cubes are 3 cubes? So in these 3 cubes, only when it says both control cubes are 1, immediately flips the target. So here, no one 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 here. Here it is. Both are ones at the control state. So immediately change the target keyword. So change it 1 1. In here, both are 1 as the control state, immediately change the target state. We can here flip the target. So flipped state here, that is for TOEFL state. Here the representation of matrix. This is the changed state. Thank you.